My soul longs to sing of transformations. But whether you are a statue turning into a person, or a person turning into a stag, or a circle turned into a wave, or a city turned into a cosine, or even if you're a solar system, the real challenge is getting yourself back. But the transformations we are concerned are even more profound than anything Ovid would write about. They're transformations from one dimension to another, from inside the trig function to the outside, from powers of x to waves of x, or from magnitudes to angles. But it's most often talked about a different way, in terms of time and frequency. Well, what does that mean? And in a way, time and frequency are inverses of each other. Seconds are hertz, cycles per second. So it sounds like you're going from a cowboy riding a horse to a horse riding a person. But slow down, partner. Now, frequency is the inverse of period. Period is a special time. It's the time for one cycle. And if you want to connect the Fourier transformation to a simpler physics equation, I'd suggest this one. Distance equals velocity times time. That's basic enough, but let's do it rotationally. Theta equals omega times time. That's the same physics and a brand new playground. Omega is angular velocity, the degrees, or the radians, traveled per second. And therefore, omega is, of course, related to frequency, which, again, is something Euler had a lot to say about. He is our master of rotations in the complex plane. Like I said, it's a new playground. EI theta tells us how far to rotate. EI omega t tells us the same thing and more. It tells us how far we rotated, what our rotational rate was, and how long it took. See that? Our quantities time and angular frequency, or you call it angular velocity, it's the same difference. Our quantities are right next to each other. So transforming between time and frequency in this equation, it seems like a smaller step, but it's still a huge leap. It's like changing from being old to being fast. Well, that's two different ways of getting there. You can either be traveling for a long time or be quick, but they're different, even though they're kind of the same. They're different, and wait a minute, this does sound like something Ovid would write about. But it gets even weirder. Negatives. Clockwise rotations. Now, I've heard of that, but how does that happen? Negative time? Negative frequency? And speaking of weird, we haven't even mentioned you, I, or you, Fourier, the complex Fourier series. We introduced this in the previous video. We connected it to the non-complex Fourier series, the one we have come to love, especially the coefficients. Love those guys. But now we want more than just series. And we want it to be tidied up with omega, whoever that is. The Cn terms are found using our functions, and the Cn terms are really what it's all about. This equation adds them up. All the waves, all the rotations, all the epicycles, an infinite number of them, all with different frequencies, clockwise, counterclockwise, but not all frequencies are allowed. Only integer multiples of some fundamental frequency, and that's not fair. We want to see the amplitudes. We want to see the Cn's for all frequencies, and I know how to do it. We will let the fundamental frequency approach 0, and we will see this illustrated, a better picture of this in the next video, which is the last video. Promise. This video is about showing that our equation works. And don't worry about the negative I omega t. That came from the Cn term. The equation, again, it's all about Cn, all about finding those coefficients. If it's truly a transform, it can be undone from time to frequency and back. More about the back again part in video 7. Hey, the 1 over 2 pi term. Who ordered that? The rest of this video, again, is the forward-facing Fourier for frequency. And, like always, if it works, we'll keep it. If it works, if it gives us the results that we found using this, which was annoying because it was so long, but was friendly. Friendly, it fit in our spreadsheets. Of course, our results won't look exactly the same. Earlier videos looked at distance from 0 to 2L. Now we're looking at time from 0 to t. And this omega gets rid of those pi over L terms. And when I say omega, what I really mean is omega 1. The first, the fundamental frequency, the frequency of which all others being whole number multiples of. End of preamble. Beginning of the square wave, the one we could control. Focus there on the center term. L over L. Fine. Omega 1 substitution. Done. This is the equation we are asking the Fourier transform to give us. This is what will make us happy. What about A naught? Well, who cares? We want frequency. Frequency doesn't care about your average height above the x-axis. Cosine n pi x over L. Well, who cares about that? We want frequency data. That's just our wave generator. You give it an x, it gives you a wave. We want the coefficients. We want the coefficients. Last major change here. See that n omega 1? Well, what does that? That generates all our possible frequencies. We'll just call it omega. And then see L, we're talking about time between 0 and t over 2. I call this Fs. It came from the Fourier series. Fourier transform can give us this. But wait, negative time? Totally cool. I ate lunch an hour ago. Negative time, clockwise rotation, totally cool. Function, Fourier. We'll wait again. All these interruptions are getting really annoying. But we need some new tools, not old ones, new tools. New trig identities, Euler's equation, replacing I with negative I and working out the details somewhere else. But these are tools. Now we get back to work. Integrating limits using this with the 2. Done. Perfect. Almost. What about that t over 2 term? What's that? Well, it's different, but it's not a problem. It's different because it's different. The series gave us a repeating pattern forever. T was the time for one cycle of that repeating pattern. The transform gives us something different, a 1 square pulse. That's all you get, 1 pulse. Again, this will be shown more intuitively illustrated in part 7. For right now, just feel comfortable about these guys being similar enough. The series is just designed to do something a little bit different. It's designed to give you the total amplitude averaged from 0 to L, or from 0 to t over 2. But that's not our only problem. What about 0 omega? Won't that destroy our function? No, it won't. Thanks to the small angle formula. A little rearranging gives us that. But what is it? The amplitude of the frequency when it's not moving? Well, sure. That's like the y-intercept when x equals 0. Or we can just think of this as a solution to that when n equals 0. Hey, e to the 0 equals 1, but beware, the 1 over t term again, there it is again. This is our function in frequency space. Enjoy it. Transformed from time. A pulse of high amplitude frequencies. Other possible frequencies. Negative amplitudes, that's okay. Roots. No frequencies at these cycles. Our equation. Let's find another one for our triangle wave. With fewer interruptions this time, I promise. Series. Clean up the center term. L. There. Distribute the negative. Watch the negatives. And omega 1 is just omega. Fs. The series result. Fourier. Function is long. Let's split it up. Integration by parts on part 1. Integration by parts on part 2. Add them together. Okay, let's look at this thing here. Those cancel out. Collect the rest. Hey, we can use the cosine substitution. Finish it up and declare success because the L term does not bother us. Could be t over 2, but the L term does not bother us. 2 equations for 2 different wave pulses, and they are more similar than you might realize. Let's use the double angle formula. Nice. And a new function, the sync function. I promise I'm not making this up, but consider it for angle alpha. Wait a minute, is alpha really an angle? Well, omega is a frequency, k is a time, yeah, so yes, alpha is a angle. Do the one on the left first. Look at it, replaced. Next, the one on the right, look at it, it's a square there, good. 2 cheers for symmetry. And one more function before we leave. The bell curve, e to the negative t squared. Very fast and loose with this one, just a conceptual walkthrough, run-through of this one, which I wanted to do. This is a good example of something that's a lot easier for me to do mechanics-wise with the transform than with the series. Getting started. Focused on the brackets. It's a function of t. complete the square. You ever done that before? Remember that? Clever. Out of the brackets again. The result, you call this a result? Yes. Stay with me here. Almost done. Stay with me. F of omega is an integral, but E is its own derivative, so E is its own integral. What I'm saying, F of omega is of the order of E to the negative omega squared. See that? F of omega is of the order of E to the negative omega squared. So the Fourier transform of a bell curve is, wait for it, another bell curve. This function is transformed into itself. It looks the same in time and in frequency space. It looks just as good in one dimension as it does in another.